Hello all and welcome back to this discussion which I would call putting it all together for week 1, right? So we have looked at various experiments but we had nothing to sort of connect all of this, right? So the idea of this lecture is to theoretically connect all these concepts and put them in a more formal background so that you can use it later on in this course. So before I start, let me just list the experiments that we did. Okay, the first thing we did was we basically studied a battery, right? We studied the battery specifications of various batteries of an iPhone, of a smaller phone, and so on, right? And just to remind you, it was 1510 milliamp hour, right? Then after that we looked at the charger specs, right? And this was more in terms of maybe 3 amps kind of charger, or you would also have something in watts, right? So if you remember, also by the way, for the battery you had a spec called some 5.8 watt hour or something like that, right? So similarly for this charger you could have a 25 watt charger, right? And the third experiment that we looked at was essentially the idea of a heater, right? So this we connected to a 230 volt source and we were trying to understand what would happen when you had current going through that heater and why it leads to heating up of the water, right? So this was a 1000 watt heater, and if you remember, we measured the voltage, albeit an alternating current voltage there, right? So we measured something like 230 volt, okay? And the result we found was the resistance of the heater was about 52 ohms, okay? So now we are going to sort of understand all these terms a little more formally, and in order to do that we obviously have to start with what is known as the electronic charge. Okay, E, and this is 1.6 into 10 power minus 19 coulomb, okay? So if you remember, if you have some sort of a charge like this, a Q, and you apply an electric field, the charge can move, okay? This is an electric field E, then the force on this charge will be Q into E, right? And how does the electric field come? It comes because of a potential that can be applied across two terminals, right? And let's say this we applied a potential of V, okay? Then there is a certain work done in moving the charge from one end to the other end, right? And that work was essentially given by Q times V, right? So these are some things that you remember from physics, right? And of course, if this charge happened to be an electron, okay, which means it's negatively charged, then the direction of motion will be opposite to that of the electric field, right? Though the magnitude of the work done and all that stuff would remain the same, okay? So essentially what happens now is, if you consider a conductor, right? If you consider a conductor like this, okay, with a rectangular cross section, okay, I'm just going to consider some arbitrary volume, okay? I am assuming that this height is, let me say, h, this is L, and or let me call this W, and this is going to be L. Okay. So what happens here is, if I take this conductor and just look at this conductor as it is, without applying any potential, there are lot of free electrons sitting here, okay, with a certain density, right? There are numerous free electrons at room temperature. At 0 Kelvin, by the way, there will be no free electrons, okay? A free electron is an electron that is available for conduction. So when you apply an electric field, this electron can move and it can constitute a current, right? So these are essentially free electrons, right? And these free electrons, just by virtue of being at room temperature, at a non-zero Kelvin temperature, have some energy and they move about randomly. Okay, so they are all moving about randomly in different directions. Okay, but of course you could ask that, if I have an electron and it is moving, right, then won't I have a current? Well, you won't have a current, because all these net currents that come out of because of these free electron movements will cancel out each other, and there will effectively be no current in this conductor, right? So this is the picture when there is no potential applied. Now when I go ahead and apply a potential here, okay, like this, what will happen is, these free electrons, which are now moving in very arbitrary directions, also start drifting in the direction of the electric field, or in the opposite direction, because these are all free electrons, right? They start drifting in a direction opposite to that of the electric field, right? And that leads to what is known as a current, right? Is essentially because of moving charges. And here we can talk about free electrons. Okay, so this thing might be a little difficult for you to visualize, but if I can borrow the analogy of Professor Karmalkar, my colleague from IIT Madras, you can imagine that you open a sweet box. Okay, you open a sweet box out here. Let's say this is a sweet box. What will happen is, you will see lot of flies, hovering around this sweet box in some time, right? And these flies are not stationary, right? They are actually moving in very arbitrary directions, right? It's actually quite amusing to see them. And these flies are just moving in arbitrary directions, much like your free electrons are at room temperature, but without applying a potential, right? So they are just stationary here, they are just hovering around the sweet box. Now you move the sweet box slowly, right? You are not going to move this very fast, okay? Even when you have a current, the electrons drift at a reasonably slow velocity, by the way, okay? When this sweet box is dragged or pulled slowly, you will see this entire cloud of, of flies actually moving along with the box. However, they continue to move in that random direction while drifting, right? So this is what we mean by a drift velocity, okay, Vd, which is essentially a velocity that these charged particles gain because of the applied potential or the electric field, right? So what you have to do in order to calculate the current is, you have to look at a cross section here, right? I am going to consider a cross section in this conductor, okay, like this, and let's say this is of length dx, the width is w, and the height is still h, right? So if I look at this elemental volume dV, okay, of the conductor there, it is going to be W into H into dx, okay? And how many free electrons do I have there? So let's assume that the density of free electrons is n. Okay, density of free electrons. Okay, so this is going to be measured in per centimeter cubed. For example, it could be something like 10 power 18 per centimeter cubed. Okay, it's 1 centimeter cubed is very large for an electron, so therefore the density of free electrons in a conductor will be something of that high order of magnitude. Okay, so typical number could be about 10 power 18 per centimeter cubed. Okay, just an example, right? So if I look at the total charge, okay, in this particular elemental volume that I have considered, okay, here you will see that the total charge is of course the electron charge, okay, E 1.6 into 10 power minus 19% coulombs, okay, into the elemental volume W into H into dx into the number of free electrons per centimeter cubed, or the density of free electrons, right? So now if you take this particular cross section and just observe how many electrons are crossing this particular volume per second, that will give you an estimate of the current, right? So all I have to do is look at dq by dt, okay, the rate at which they are going, E into W into H into N into dx by dt, right? So what is dx by dt? It is the rate at which these electrons are moving, or the speed at which these electrons are moving. Okay, so dq by dt is, which is nothing but the current I, is going to be E, and I will say this W into H is the cross sectional area, okay, E into A into N into drift velocity, right? Remember, this drift velocity is exactly analogous to what the flies would do if you drag that sweet box, right? So this gives you an estimate for the current straight away, right? So later we will show you how you can estimate the resistance of a conductor also in a similar manner by taking this derivation forward, right? So if you look at the electron here, we said it was coulombs, right? So it was measured in coulombs, and current is measured in amperes, right? And it's very easy to see that ampere dimensionally is nothing but coulomb per second. Okay, so this is very important. We have to deal with all of this in the SI units. So I cannot be using hours here, for example, right? So therefore, if you look at this thing, ampere into second is nothing but coulombs, right? It gives you charge, right? So I into time will give you some estimate of charge. So one interesting experiment that we could do was to take this battery that we were describing in a previous lecture, right, which had a rating of 1510 milliamp hour, right? So you see, by the way, that milliamp hour is nothing but current into time, except that it is not measured in terms of the SI units, and therefore this whole thing needs to be brought down to SI units if you want to measure how many coulombs of charge there is going to be, right? So let's do that calculation. We are looking at 1510 into 10 power minus 3, because the milliamp is going to be, I'll leave the amperes as it is, okay, and hour has 3600 seconds, right, and therefore this is going to be I can just absorb this 10 power minus 3, 1.5 into 3600 ampere into second, okay, ampere, let me write it as ampere into second here, and this is nothing but coulombs. So how much of charge did that battery actually have if it was charged fully 100%, right, with to a first order at least, right? Then how much of charge would it have? It would be 1.5 into 3600 coulombs. Okay, remember this is actually a very large amount of charge, and it's not surprising, right? Because if you remember, you know, the stress test of that battery, right? What did they say? If you watched video and you also browsed the internet for 1 hour and you also made some calls for 1 hour, you would have to recharge this battery fully 100% once every 54 hours, right? Now 54 hours is clearly over 2 days, right? So that's a long time, okay? Clearly you need a lot of charge, but that is how much that, you know, small battery is able to store and provide for all your activities, right? So you have these many coulombs of charge, and we could evaluate this if you wish to get the exact number. Okay, so 1.5 into 3600, it is 5400 coulombs of charge. Okay, remember the charge of an electron is 1.6 into 10 power minus 19. E is 1.6 into 10 power minus 19 coulombs. So the number of charged particles that this battery is actually storing is very, very high. So if you want to get that, you will have to divide this. The number of charged particles will be the total charge, 5400 coulombs, divided by 1.6 into 10 power minus 19 coulombs, right? So if you look at this, the coulomb will cancel, and you will get approximately, forget all this, you will get about 3000, right, into 10 power 19. Okay, that's how many, that's how much of charge, you know, that's how many charged particles you need. Okay, and just as an interesting number, if you remember, if you take 1 mole of electrons, okay, that is 6.023 into 10 power 23 electrons. The amount of charge that is stored in that is going to be 6.023 to 10 power 23 into 1.6 into 10 power minus 19. This is approximately 96,500 coulombs of charge. Okay, so if you look at the number here, we had about 5400 coulombs, which is about half that, and that's exactly what we are getting from our calculation as well. You get something like 3 into 10 power 22. Okay, so approximately we are sort of there in terms of order of magnitude again, right? Okay, so after that, what we discussed was you had a voltage source, right, and you had an arbitrary circuit. Okay, I don't know what is inside the circuit for now. Okay, and this is the battery. Okay, so what you are trying to do now is assume that a charge dq enters this particular block, right? It's an unknown block, right? Unknown block. It could contain anything. It could contain resistors, capacitors, inductors. It could contain ICs that do different things. It does not matter, right? There is a charge dq that entered. Now, if that dq entered, then dq must also come out of this. Otherwise, there will be charge accumulation somewhere, because some charge has gone in, but not all the charge has come out, which means charge is accumulating somewhere, right? And that can never happen, right? You have to follow the fundamental law of nature of conservation of charge, and therefore that can never happen. So assume that this battery here, you are using a potential of V, right? So then if you remember, we said that the work done in order to take this charge around was V into dq, right? And what is the rate of change of work, of energy? dW by dt is nothing but power, okay? And this power therefore is V into dq divided by dt, which is V into I. Again, rate of change of charge is going to give you current, and therefore V into I is going to give you power, right? And this is what we had called watts of power. It was the dimension of power was in watts, right? And dimensionally watts is equal to ampere into volts, right? So just going back to our battery charger, right? Our charger, we said that this charger could provide 3 amps of current with 25 watts. Okay, so what it basically means is that you are able to provide a voltage, right, which is going to be 25 by 3 amps, approximately 8.33 volts, okay, with a current which can be supplied, which is 3 amps. Okay, this is essentially your charger. So remember that we had also discussed that watts essentially was telling us the rate of charging, right? So that's what you see here. It's the rate of charging, and for a charger what really matters is only the rate of charging and not the total amount of charge. So earlier, if you looked at a battery, for example, what we saw was we were worried about the total charge that was stored in the battery, because that's a fixed energy source, right? If this charge is gone, then I have to go back to a charger. Therefore, the battery will always be characterized with the amount of charge, or alternately you could also do it in terms of the total amount of energy, by the way, right? So for example, this same battery that I took, if you remember, also had an alternate unit, right, which was about 5.8 watt hour. Okay, the battery, the charger, by the way, has a specification of watts, right, whereas the battery is sometimes can also be specified in terms of 5.8 watt hour. And if you remember, the battery was giving us about 3.8 volt. Okay, so you take this 1510 milliamp hour and multiply it by 3.8 volt, then what you get is 3.8 into 1.5 is approximately 5.7 watt hour, right? So what you see here is this watt into hour. If you wanted to convert it to SI units, then of course you have to take this hour and multiply by 3600. Then this 5.8 will become 5.8 into 3600, right? This will become watt into seconds, which is nothing but joules, which is the unit of energy, right? And now coming back to the argument of the charger versus the battery, what we saw is that the charger is actually worried more about the rate at which energy can be pumped into this battery. You know how fast you can charge the battery. So therefore it is joules per second. How many joules of energy can you provide to that battery per second, right? And that's why it is characterized primarily in terms of watts and sometimes in terms of the current. If you fix the voltage, then equivalently you can specify this number as a current, right? So moving on from here, what we did after this was to look at a source, okay, and look at a resistor, okay. This was V. So one important thing we have done till now is that we have been looking only at DC sources, okay, which is direct current. What does a DC source mean? It means that voltage is a fixed number as a function of time. So if I plot the voltage as a function of time, on the x-axis I am looking at time, on the y-axis I am looking at voltage. Let's assume that this is a 5 volt battery, V1 equal to 5 volts, and if I plot this voltage, I will get this much of voltage. So this will be 5.0 volt, okay. There are other time varying voltages that we will look at later, but we will come to that at a later point in time, okay. So what happens now is when we look at a voltage source that is driving a resistor, right, we are going to get a current from the voltage source, right, and approximately this is what we did with the heater, right, or the kettle example, right. And if you remember the measurement that we made, we basically had, we used a voltmeter, remember, and we got one number called 230 volt, okay. And the resistor that we measured, again when we measured the resistance of that heater, we got about 52 ohms, right. And therefore what we wanted to know was how much of power is being delivered by the source, okay. I have to mention here that this 230 volt is not a DC source, it's an effective DC value that we can use for now. Later we will explain what that alternating current source is and how we can derive this equivalent DC number, okay. So let's not get into that for now. So there is a 230 volt source with a 52 ohm resistor, and what we want to know is what is the power delivered by the source, right. So this we already saw was V into I, okay. Now what is I? If there is a resistor, right, if we have a resistor with a voltage, you know, with a voltage V across it, then the voltage is nothing but V into IR, okay. Now therefore if you look at the total current through this circuit, it is nothing but V by R, and therefore the power is going to be V into V by R, which is equal to V squared by R, which is 230 volt divided by 52, okay. So again let's make this calculation, okay. 230 into 230 divided by 52, you get approximately 1000 watts, Okay, I am not worried about this 1017 and all that. It's approximately 1000 watts, right? And that is exactly what we saw in that kettle specification as well, right? So essentially what we did was to validate all these theoretical equations using some experiments, right? In the coming weeks, we will look at more advanced concepts of network theorems and capacitors and so on.